Okay, thanks everyone for coming here. We're very excited to have Kevin speak to us today. Probably Kevin doesn't need an introduction. He did his master's, I think, in the US already, did you? At UPenn, if I remember correctly. And then his PhD at Berkeley. But before that, he was on these aisles, so it's a glorious return, hopefully. And yeah, and then he was at UBC for, I think, a couple of years until 2012, and he's joined Google-Deepmind since. And he's been quite happy there, apparently, and quite productive, as we all know. I think the textbooks are standard references, and if you're anything like me, that's how your journey into machine learning started. So without any further ado, Kevin, thank you very much.
Great. Thank you for the invite. Great. So thanks everyone for being here. It's my first time at UCL. It's kind of fun to be here. So I'm going to give like a big picture talk about like all of machine learning. And why am I doing that? Well, I think you know that machine learning is taking over the world. It's in the news every day, tons and tons of applications. And if you look at the number of papers that are being published in the field, it's just insane. It's just growing more faster and faster. And it's kind of hard to make sense of the big picture and find the woods for the trees. So I wrote a series of books on machine learning, as Professor Novak just mentioned. And in order to write these books, especially I'm going to focus particularly on this advanced topics book that just came out, I had to have some story to try to make everything cohere together. So that's the story I'm going to try to tell you today. And so, is that beeping coming from me? Yes. Oh, is it people joining Zoom or something? Yeah, these people. Should I get out of Zoom? Oh, thank you. I'll be right back.
Yeah, no, it's not on.
So, it's not good. Sorry. I don't know. All right. So we'll ignore the Zooms. Anyway, give me time to oh, it's really bad. The things I don't know, but they're from Zoom. So these are the books I wrote. They're all available online, or at least the new ones are available online for free, and they cover like the whole field basically. So but like this advanced book is, I think 1,300 pages. So I wanted to, and that's a compression of the field. So I'm going to further compress it into what I'm calling the 4 pillars. And these are what I view as sort of like the principal components of the field, basically, that span more or less everything that people do. And it's like I think, a nice conceptual framework to try to think about how different parts of machine learning relate to each other. So I'm calling them predictions, decisions, analysis, and synthesis. And essentially, so I'll go through these pillars one by one and give some examples of problems that fall into this sort of bucket. And they're all going to be, they can all be viewed as like different instantiations of certain, they can all be viewed through the lens of decision theory as a sort of grand unifying framework that I'll present shortly. But if we start at the very basics, we get prediction problems, right? So this is just supervised learning. And, you know, if it's a linear model that you'll take in your stats 101 class, sure, you all know these things, linear and logistic regression. And now you can make them nonlinear. And of course, once you decide to be nonlinear, then there's many ways to define nonlinear models, right? There's classic tree models. Neural nets are all the rage these days, but there are like Gaussian processes and many other kinds of nonlinear models, or kernel methods more generally. So you can do all that, and that's great, and has lots and lots of applications. But, you know, you could be a skeptic like this guy here, Judea Pearl, who has a Turing Award and has done pioneering work in the causal inference field and other fields as well. And he said all of this fancy stuff is just glorified curve fitting. And technically, I think that's true. But I think it's a little misleading, because when you hear the word curve fitting, you think of something like this, like a curve in 1D. And this is kind of boring. You know, you could just use a spline, right? Why do we need AI? This is not AI. But once you move to high dimensions, it becomes a little less boring and a little less non-trivial, even though technically speaking, it is just curve fitting. So I did a bunch of work in the past in computer vision, which, you know, you could abstractly think of as a curve fitting problem, where the input is an image and the output is a set of key points of people, and you want to do pose detection and maybe track them over time. And that's a curve fitting problem, but like, that's a little bit unfair, I think, to the the thousands of people in the computer vision community who've worked on this and the importance of this problem. So yeah, so that was like static image recognition. You can try to do forecasting in time. And there's like tons and tons of these applications. And maybe they are all just curve fitting, but like that's actually, you could do a lot of things with curves. Okay, so these applications, you all know about this, and it's kind of amazing how far we've got, I would say. And there are claims that, you know, now we're beating humans. Okay, so is the problem solved? Well, not always. In fact, some of these systems are actually extremely delicate and brittle, and they can break at, I want to say the drop of a hat, but you can change the operating conditions by just a small amount, and suddenly the system might fail. So, you know, your digit classifier performance might drop a lot if you just rotate the digits, or you add noise to the image in a way that wasn't expected. And you know, if you train on more and more data, the systems do become more and more robust. But you can't cover the long tail with data alone, is my claim, right? That's just playing whack-a-mole. The system breaks, you pour more data on it, you fix that problem, and then another problem shows up. And this is obviously not going to be acceptable for high-stakes problems, like in the medical domain or self-driving cars. So basically, the high-level story here is that supervised learning and predictive modeling is great, but it relies on the IID assumption, and that isn't true in general because distributions always change, or nearly always change, and that requires fundamentally new methods that people are studying, but only recently. So just to do a deep dive into one example in that space, I'm going to talk about a paper we have recently focusing on a specific kind of distribution shift that's been studied a lot recently, which is to do with this phenomenon called spurious correlations. So this is the problem, right? So you can get a bunch of images of, let's say, labeled with cows and camels, and you can train whatever nonlinear model you want, like random forests or CNNs or whatever, transformers, and you can get perfect performance. But then you can get an image like this, and it will confidently classify this as a camel. Okay, where it clearly is not a camel. So why do these models fail in that way? Well, it's because of the data that they're trained on. So the data sets that these systems were trained on, nearly all the camels were in deserts with sand in the background. So these models recognize that, oh, whenever there's a camel, there's a large number of yellow pixels. So I don't actually need to look for the shape of camel. I just need to count how many yellow pixels there are, threshold on that, and I'll get 100% accuracy on the training set. And that's true regardless. It's even a linear model failed this way. It's not a flaw of deep learning. It's a flaw of the fact that the data has this bias that is like a fragile but easy to exploit phenomenon. So if you change the data so that suddenly there's a cow on a yellow image, then the systems will fail. So you need to model the fact that the distributions, there might be properties of these images, or in general the input data, that are correlated with the target label, but they're not correlated in a robust way. So it's a spurious correlation. The background is spuriously correlated with the label because of the nature of the training set, but that's not a stable property of the world. It might change at runtime, and your system will fail, and you want to account for that. So here's a more real-world example of that in the medical imaging domain. So these are chest X-rays where the goal is to detect pneumonia. And it turns out that the sex of the patient is highly correlated with the disease status, at least in certain data sets. And it's easier to do sex diagnosis than pneumonia diagnosis, as you can see from these images. And so the systems basically learn to classify if the patient is male or female, and they don't, and that is highly correlated with the disease status. So then if the target population, the sex ratio changes, then the system might break even if the underlying disease hasn't changed. So you can think about that from a modeling point of view if you draw a little graphical model of what's going on. So you've got your data here, your X-ray, and you've got the class label, which is the disease status. They either have, it's a fusion or they don't have a fusion. And there's the sex status, male or female, which is spuriously correlated in the training set with the disease. And these two factors together generate the image, right? So there might be other factors that we're not explicitly modeling, but if you know the disease status and you know the sex status and other conditions like lighting or whatever that are not explicitly modeled, then you can generate the image. But these two Y and Z variables are correlated due to some hidden common cause, U, which we don't see, but they're correlated in the data. Maybe it's a military hospital and most of the patient population is male, and then you go to a regular hospital and it's like 50-50 or whatever, right? There could be any number of reasons why there's a correlation between these factors in your training set. That might be an unstable correlation that changes, and that's what this lightning bolt represents. Like that, this part of the model might change, but we're assuming that the physics of the model is invariant across everywhere in the world. So if you know these factors, then the mechanism that generates X-ray images is the same, whether in America or England or in India or something. But the patient population, of course, mixes, right? It changes according to the distribution. So if you do the usual thing, you would train on your source distribution. And let's suppose that in the source distribution, there's say a 10% correlation between female and having the disease. And if that's your test distribution, you'll do quite well because these models have high performance. But then as this correlation parameter changes, the performance of your algorithm will get worse and worse. So I'm plotting here the area under the ROC curve versus the degree of correlation between these two variables, y and z. And so as the correlation changes away from what you trained on, performance of your IID model will get worse. So this is the problem we're trying to tackle. We want to be robust to these kinds of changes. Okay, so the standard thing in the literature is you one approach that's quite common is distributionally robust optimization. So rather than just minimizing the loss with respect to the parameters, you minimize the expected loss where you're taking expectations over perturbations of your distribution, right? So these are distributions that are not just the ones you've seen, but things that you might encounter in the future. So you have to define some set of potential distributions that you want to be robust to. So one way to do that is to stratify your data not only by the target label, but by a set of meta labels or group labels, which are these Z terms here, which in our example are the sex of the patient. And so you're going to get different subpopulations. And what you're saying is you want to minimize the worst case performance across all possible groupings, right? And that will give you a robust optimization objective. So you can do that. Yeah.
You're in front of the equation.
Sorry, that's a very good point. Okay, so this is the group DRO objective, as it's called, group distributionally robust optimization objective. And this is being used a lot in the literature, and it works quite well. But the problem is it's sort of it's a min-max objective, so it's a worst case thing. And so basically what we're doing in this paper is we're going to try to be lazy. So we're not going to try to model up front all the possible changes that are going to occur. We're going to wait until we get some data from the new distribution, and then we're going to adapt our model to the new distribution in an unsupervised way, and then we'll make predictions. So we're going to do test time adaptation instead of training time robustness. And this is basically, we'll show that this gives improved performance. So the work I'm talking about is going to be presented at NeurIPS in a few weeks, I guess, in New Orleans. And this is work I did with a student at Chicago, Jingyao Sun. So this is the key idea in one slide. So the modeling assumptions are the same as before. So we have these latent, well, we're going to assume these factors Y and Z are not latent. We're going to assume we have labels for them. So it's a supervised problem. We know the class label. I'm also assuming we also know the group label, which is a strong assumption, but we're going to make it. And other people have made a similar assumption. So what do we want to do? We want to predict the class label given the inputs X in the target distribution Q. And Q is different than P. So P is the source distribution that we train on, and Q is the new one that we encounter in the wild. Okay, so we can just compute that by marginalizing out this joint distribution. How do we get this joint distribution? Well, Bayes' rule says it's the likelihood times the prior normalized. Okay. This likelihood term, this is the first key assumption. We're going to assume that the likelihood in the target distribution is the same as the likelihood in the source distribution. So that's our causal invariance assumption, which is like the physics of the world doesn't change, but the prior terms might change. Okay, so how do we compute this likelihood? Well, X is a high-dimensional image. We could fit a conditional generative model using, I don't know, diffusion or a VAE or whatever, but that's complicated. And it's unnecessary in this case because we only need the likelihood up to a constant factor because we're plugging it into computer posterior. So we can flip things around. I call this the discriminative likelihood trick. So by Bayes' rule, once again, the likelihood is the posterior times the prior. And this is just a discriminative classifier. right? It could be anything, a neural network or decision tree. So where we predict both y and z jointly given x. So these are just two discrete random variables, and x is some high dimensional thing. So we can fit a discriminative model to that using standard supervised learning, anything you want. And this p of x term is going to cancel because it's a constant. And this p of y and z is the distribution over y and z in the source. And these are discrete variables. We can estimate it just by counting, right? So let's look at the terms. We've got this supervised discriminative model trained on the source distribution. We've got this prior counting thing from the source distribution. So they're easy to estimate using any method you want. And the only thing we're missing is what is this new prior in the target distribution, this QYZ term. And if we knew that, we're done. Problem solved, right? So that's the only problem that we have to solve, is how do we compute this term here? Okay, so trick number 2 is to squint and say, okay, let's just glom these y and z variables together into a single variable. We'll call it m. And m stands for mixture. And now it looks like a mixture model. It's not all neural nets, you see, if you've taken your classes on GMMs or whatever, this is like you've got a latent discrete variable generating some high dimensional output. The likelihood function is given to us. We know it already, right? It's our discriminative model inverted. So all we have to do is estimate the prior on our mixture model, and we can use EM for that. And it's super fast. This is the few iterations. And in fact, you can prove that the objective is convex, so you'll get the global optimum. And you don't have to use EM. You could use any estimator, right, applied to that convex loss. But EM is super simple. So what you're doing is you're just estimating the joint occurrences of these labels in the unlabeled target distribution. So in an unsupervised way from this model. And once you've done that, you can plug it into this equation, and then you can make predictions at test time. So that's how we adapt our model. So we train on the source data. At test time, we get a little bit of unlabeled data. We run EM, and then we predict. And this is what happens if we measure performance at that method. So this data set is the colored MNIST data set. So here, the goal is to classify that it's either a 9 or an 8, and the color of the background is spuriously correlated. So in the training set, like 90% of the 9s are red, and in the test set, 90% of the, K% of the 9s are red. And K is going to vary from 90 down to like 0.1. So we're sweeping that correlation parameter along the x-axis, same as before. And if we just train our usual CNN, say, and test it, we get the black line and the performance drops off like we saw. If we do the min-max thing, we get the flat curve. And lo and behold, it's invariant to the distribution shift as promised, because it's a robust estimator that's invariant by design. But our blue thing is adaptive. So this is Bayes beats minimax, right? Because we're adapting to the distribution at runtime. So this is our blue algorithm. So if there is correlation in the data, then we can adapt to it and exploit it to get additional juice compared to a method that's invariant to that correlation. So that's basically it. We applied it to the medical data set and get essentially the same results. And we've tried it either on raw pixels or on beddings where it's all linear modeling and it's very fast, and both of those work. And we also applied it to, we used this random forest as well as neural nets just to show that it's completely black box. Whereas a lot of the papers in this literature, there are a bunch of like neural net hacks that only work if you're working with neural nets, and this is completely generic. And I mentioned earlier that I'm assuming that the group labels are known. It turns out you only need a tiny amount of group labels, and then you can like impute the rest using EM once again, or some other imputation method. So you only need like 5% of the data to be labeled, strongly labeled, and the rest you just need the standard labels. And in fact, you can prove that if you don't have any labels for the groups, then it doesn't really work because you get unidentifiability problems. Okay, so that was a little vignette. That was vignette number 1, and I should be watching the time. 1 of 4. So popping up a level, that's just one drop in this big ocean of distribution shift, right? So, but I think it's an important problem. Like there are many benchmarks now that create data or sample data from different distributions, and you want to like train on, I don't know, animal identification in colored images in, that looks like England, doesn't it? And then maybe you want to test on black and white from close-ups or whatever, right? And magically you're hoping this will work. it's not clear that there's any reason why it would. Or maybe you've got like staining of tissues, and the staining methodology is different across labs. And maybe a human expert can be invariant to a color, but the machine isn't. So you want to be robust to that. So there are lots and lots of applications. I'm not claiming that our spurious correlation methodology is sufficient to tackle all of these kinds of shifts. I think in general, the way in which distributions shift is extremely diverse and will need different kinds of assumptions and modeling techniques to tackle. But I think it's an interesting area, important area to work on. Okay, and it has some connections with causal inference as well, which I think is an additional tie-in that makes it interesting. Okay, so let's move on from prediction. So we can do supervised learning. We can add some sugar on top to make it robust or invariant. But ultimately, we're still just making predictions about outputs. And in many problems, we want to go beyond that, and we want to make decisions. I thought this slide came earlier, but never mind. So now we're going to move on from just making predictions to making decisions. So we're going to do that using tools from Bayesian decision theory. The frequentist approach is similar, but this depends on what you're averaging over. But in the Bayesian decision theory approach to the world, you assume there's some unknown state of nature, H for hidden, and you're this little agent or policymaker, pi, and you get some data from the world collected by your measurement device, observation O, and you have to choose an action A from some action space. And after you've taken your action, then nature either rewards you or punishes you, so you incur some loss. And the goal is, if you want to be an optimal decision-making agent, you want to minimize your posterior expected loss, right? So you want to pick the action A such that the loss that you incur is as small as possible, but you don't know what the loss is because you don't know what H is, it's hidden. So you take expectations of H conditioned on the data that you've observed. And that's what makes it Bayesian, right? Because we condition on the observations. Equivalently, we can maximize expected utility. So that's the framework. So this is a completely general framework that will encompass all four of the pillars. So to see that, let's now revisit prediction from a decision theory point of view. Well, it's pretty simple, right? It's just a change of notation. So the unknown state of nature is the unknown class label. The observation is the test feature vector plus all your training. The action is to just, your policy is the predictive model. The action is the output of your predictor, like a label. And then the loss, well, it depends on the problem. It could be L2 loss or 0, 1 loss or something. So the optimal action is to predict the label that minimizes posterior expected loss. And yeah, so if it's L2 loss, you pick the posterior mean, that's regression. If it's L0, 1 loss, you pick the posterior mode, that's classification, right? So that's a special case. But the nice thing about decision theory is that you now can consider actions that are more general than just prediction. So you can say, fine, I can predict if you have the disease or not, but I'm going to give you an extra action that is like the unknown action or the reject action that says, well, I'm not really sure if you have a disease or not. So if I'm not confident enough, what I'm going to do is ask for help from a human expert. And so that's not in your label set, but it is in your action space. So if you define a loss function so that if you refuse to classify, you incur some loss because you have to phone the doctor and they're going to charge you $100 an hour. If you don't call a doctor and you make a decision and you get it right, there's no loss. But if you get it wrong, there's some other loss that you incur, right? And you write this down, and then it's a standard homework exercise to derive the optimal estimator. And the result is very natural, right? If you're sufficiently confident it's class 1, you should do that. Say it's 1. If you're sufficiently confident it's class 2, you should say it's class 2. And if you're in between, then you should say, I don't know, and go ask the human for help. And the thresholds are a function of, well, here is the equation. This is the magic threshold. It depends on the relative cost of refusing to classify compared to making an error, right? So, so that's the optimal thing to do if you know the model. So, so you can do lots. You can have lots of fun games with these, one-shot decision problems. But it becomes even more fun once you start making sequential decisions. So you take an action, and then the world changes, and now you have to take another action. And so this opens up Pandora's box of sequential decision making, which is a huge, huge field, which is basically the same picture as before, but now we've got a cycle. So you incur your loss and you go back, and now you repeat. So you have, let's say, if it's a finite number of decision steps, you want to minimize your expected loss over a whole sequence of actions. and the sequence depends on your policy, which is a function of everything you've seen up until now and all your previous actions. Okay, so now this is like a completely general framework. And so you need to break it down by making different assumptions about the form of the world model and the form of the policy and the form of the loss. And whether you know the model, you have to learn it online and yada, 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 right? And this will include, you know, optimal control and experimental design and reinforcement learning and, you know, all of this stuff, right? So it's super general. So I have no time to cover all of those things, right? So I'm just going to deep dive into one very special case that I worked on recently, which is still an interesting special case. And this is called Contextual Multi-Arm Bandits. So it's the same picture as before, but the key difference is that when the world just evolves randomly, it just, every time step, it gives me a random state. And these are drawn IID for some fixed but unknown opposite distribution that I don't control. It's like nature just throws stuff at me and asks me to respond. And what do I do when I respond? My response is I can pick one of K arms. So I'm imagining that nature is like giving me a set of slot machines that I can play, and I can choose. So it gives me a machine of a certain kind, and I can choose which machine I want to play. That's like pulling an arm on the slot machine. So I have a finite action space. And then when I take the action, I get a reward, which is like the payout from that slot machine. And I don't know what the reward is. The reward is an unknown function of the world. And by playing this machine a lot, I can estimate its return. And then I go onto the next machine and estimate its return. And all of these returns are a function of the environmental state. That's what makes it a contextual multi-arm bandit. Okay, so that's the problem setting. It's a special case of sequential decision making. And why should you care? Well, this stuff actually is used all over the place. So it's used in web tech companies for recommender systems and selling you ads and books and songs and everything. It's like all over the place. This is like making billions of dollars. It also saves millions of lives for use in clinical trials. It's related to Bayesian optimization, which is like an infinite version of this. So it's a very, very broadly used model family. Okay, so why is it interesting from a sort of methods point of view? Okay, so the key problem is I've got this bank of slot machines I can play. I could like pull this one 100 times and then get a really good estimate and say, you know, it's giving me, I'm playing $1 per play and I get, you know, 95 cents out every time I pull it on average. Okay, that's a loser machine. Then I could go on to the next one and maybe it's giving me, you know, $1.01. This one seems a bit better, but maybe this machine is going to pay me out $2, right? So I have to decide, should I keep playing the machine that's paying out $1.01, where I am making money, but not a lot? Or should I try this new one that might be better? Well, maybe I try it once and I don't get anything. Okay, but maybe I was just unlucky. So I could try it again and I get 10 cents. Well, maybe I'm unlucky. Maybe I try it again and get $100. Woohoo! But maybe that was just chance. So how many times do I need to pull it until I'm sure? So this is called the exploration exploitation dilemma. So I need to explore new things to collect data about the world, but I'm leaving money on the table, right? Maybe there's a much better machine, or I should have gone back to this one that's a sure bet. So there's this fundamental trade-off that comes up in all of these problems. So there are many solutions to this, heuristic solutions. The optimal solution is intractable. So a standard heuristic solution that has various nice theoretical properties is called upper confidence bound. And it's very intuitive. It just says, compute the mean estimate of the reward for every arm, and then also compute an estimate of your uncertainty. And now be optimistic in the face of uncertainty. So assume that this arm is going to pay out the mean plus some number of standard deviations. And now pick the arm that has the highest upper bound on its expected reward, right? And that will encourage you to explore things that are unknown. And then when you collect more data, your uncertainty will go down and you'll have a more and more precise estimate. And in the limit, you'll end up pulling the arm that pays off the bet. Okay. So to do this, we need a predictive model of rewards, but we need an uncertainty model as well. And there's another approach you can take called Thompson sampling, which also has nice theoretical guarantees. It's a little harder to explain, but basically if you have a distribution over your parameters, you can sample from that, plug it into your model, and then pick the action that maximizes the plugin estimate. And this also is like optimal. So both of these methods need some model of uncertainty, and that's what we want to tackle now. Okay, so in part one, we had predictive models, and maybe we could get away with point estimation, but now we really care about uncertainty because we're sticking in a decision-making loop. So if our bandit is a linear regression model then the parameters are just the regression coefficients. Let's say it's 1 per action. So it's linear function of the state. And if we put Gaussian priors on everything, we have a Gaussian likelihood. The posterior is Gaussian, and the update equation is closed form, right? And it's like equation 27.252 in my book, or whatever. It's on Wikipedia. It's like standard thing, and it's kind of hairy, so I won't write it up. But the thing is, it's closed form, and it's simple and fast. But this is a very limited model family, right? This is a linear model. So what we want to do is work with nonlinear models. No problem. Okay, thank you. So this linear thing you can update incrementally, right? You have a belief state, which is the distribution over the unknown parameters, and then you take an action according to one of these heuristics. This is the input S, you get the reward R, this is the action that you took, and then you update your belief state, and then you continue. Okay? And this is optimal because it's all exact, if your model is correct. But of course, this model will never be correct. So we want a more generic model. And now the question is, how do we do something analogous? We want to do, ideally, something fast so we can incrementally update our belief state as the data comes in. And we can use our belief state for decision making. So one thing you can do is you can think of the parameters of the model as unknown random variables that evolve over time. And at each time step, they generate observations as a function of data and actions, if it's a controlled Markov process. So these are like the rewards, and these are like the actions and the states. And the W's, I was calling them thetas earlier. Sorry, my notations, I'm mixing and matching slides. These are the parameters of your unknown reward model. And they may evolve over time according to some dynamical process, or maybe they're just unknown constants that are static. And you have a likelihood function that depends non-linearly on the unknown state, right? So this is just a non-linear Gaussian state space model, okay? This is another classic model family that's been studied for decades. And so in principle, you just turn the Bayesian crank. So how do you do that? You first predict the next step by integrating out the past, and then you use that as your prior, and then you multiply that prior by your likelihood, compute the posterior, and you're done, okay? That's the Bayesian crank. The problem is that it's very hard to compute these integrals. So one thing you can do, which is like a classic technique back to the 60s, is you can just linearize your model. And now it's a linear Gaussian model, and it's all closed form. And this is an extended Kalman filter. And certain people, Julia is crying in the audience, because this is a very crude approximation. But it works really well in many problems, and it's super fast. Well, in some cases, it can be fast. So this is a demo. This is a demo that Gerardo, I think he's in the audience. I'm working with Gerardo Duran-Martin, and he made this demo. And what it's showing is fitting a shallow neural network to for a 1D regression problem to a streaming data set. And you can see that, okay, so initially, the white dot is the current observation, and the other dots are the previous observations. And as the data streams in, the model, the posterior is converging to some, I won't say it's the true posterior, but some tight approximation around the MLE. And you can see that it's becoming a good fit. But at the beginning, I'll wait for it to reset. At the beginning, when you don't have much data, if we draw samples from that posterior, you can see that they're suitably broad, right? And then it collapses it. So this is like perfect for our bandit problem, right? So are we done? Well, the problem is it's slow. So the Kalman filter, or the EKF, it's either cubic in the output dimensionality or it's cubic in the latent state, depending on which version of the matrix inversion level you use. So here are all the equations. I'm not going to really walk you through them, but you see some matrix inverses popping up here and there. So in our setting, the output is like one-dimensional. It's a scalar reward. So we're quadratic in the number of states. So how many states are there? Well, there are as many states as there are parameters in your neural network. How many neural network parameters are there? Well, it depends. But like here, I don't know, 500,000? Not in the 1D regression problem, but like you'll see some examples later where we're doing MNIST. So it's a little MLP or a little neural net. It's got like 500,000 parameters. But these days people fit billions of parameters, right? So we can't be a billion squared. This is per time step as well. So what are we going to do? Well, one thing we could do is like say, well, forget all this base. Let's just do online gradient descent, right? We don't just compute a point estimate and update it incrementally online. Why not, right? That's a very sensible thing. Okay, what's the problem? Well, first of all, it's ignoring posterior uncertainty, so we can't really use it inside of Thompson sampling or UCP, or at least not in a straightforward way. And then secondly, it's actually very slow learner. It takes a lot of data for this to converge to the MLE if you're just doing a single pass. And you can see that in this animation that Rado made. It's just like, even if you tune the learning rate, it just adapts very slowly, which is not surprising because you get one data point and you take a tiny little step in parameter space. And the size of that step is controlled by your step size, and you're not going to learn very efficiently. So a common hack that people do is they have a replay buffer and they store the last K observations. And then every time step, you just do a few sweeps over K observations and then you move on. So obviously that's slower, but it's K times slower, but it works a lot better. You can see this is, clearly evolving more quickly. It doesn't give you a posterior estimate, but we're going to use this as a baseline. This is actually a very strong baseline that works very well in many settings. But we're going to do better than it nonetheless. And how do we do better than it? Well, we're going to take the EKF idea and say, look, the reason it's expensive is that we're maintaining a full covariance matrix. So, okay, well, let's try to approximate it. So we could do a diagonal covariance, and that's been done. That doesn't work very well. It's basically no better than SGD because it ignores correlation amongst the parameters. It's just, diagonal covariance matrix is like Adam, right? It's a per parameter scaling coefficient. So we want to capture correlation. So we use a diagonal plus low rank approximation to the precision matrix. And this has been studied before in the literature, not surprisingly. But the previous approaches compute this approximate posterior using stochastic variational inference. And that is a Monte Carlo estimator that's quite high variance. So what we do is we notice that if you linearize it, then you can compute everything deterministically. And I'm not going to have time to explain all the details, but the basic trick is we start by our induction. Our prior is low rank plus diagonal, and we choose the rank, whatever we can afford. We call it rank L. And then we do a one-step, we linearize, we do a one-step Bayesian update. The rank increases by the observation dimensionality. So now we're outside of our model family. And then we just do SVD to project it back down to rank L. And then we repeat. So we do basically EKF plus SVD plus EKF. And we sandwich those. And that's the algorithm. And it's very fast. So it's linear now. It's quadratic in the rank that we choose, but it's linear in the parameter size. So we can scale to much bigger neural networks. And we're maintaining some notion of posterior uncertainty. So we can plug it into our bandit algorithm. And this is a plot Harada made where we are doing MNIST. So this is image classification. And the action space is, you've got 10 arms you can pull, which is the 10 labels. And if you pull the right arm, you get a reward of 1. And if you pull the wrong arm, you get a reward of 0. And you can see that our method, which we call low rank filtering, lo-fi, is outperforming a previous SOTA baseline, which was called the neural linear approach, which does another very obvious thing where you do SGD of your feature extractor, and then you do Bayesian linear regression, aka karmic filtering, on the last layer. So that's like a very standard approach that people use, and that's been shown to work very well. So we outperform that. And it turns out that baseline approach is really no better than just doing greedy approximations, epsilon greedy. So which was, people didn't do their baselines properly in prior works. So anyway, okay, so this works. This is kind of nice. It's a little annoying though, because like modeling the reward function as Gaussian in this setting is very unnatural. In many bandit problems, people use Bernoulli bandits because you've got binary actions. You either click on the add or you don't, right? That's the most common use case. Or the patient dies or they don't, right? Or you have this number of patients die, you have a Poisson distribution. So we want to be able to handle non-Gaussian observations. So in general, we might want exponential family likelihoods. And I think I'm not going to have time to go through all of this, but you can generalize EKF to work with the exponential family with various approximations. And it all goes through. We're building on this work by Yann Olivier. And just to give you some eye candy, here we're using the same machinery I just described, but we're doing online binary classification instead of regression. And you can see this is another plot Harada made. It does the right thing. I don't know if it's the right thing. It does something reasonable. And just if you compare that to say SGD, if you do like one sweep over this data set, then EKF method would get you a very nice decision boundary. If you do one sweep of SGD, it's really, really bad. Now, if you store the data and you go and you just beat the crap out of it by doing, well, you're just gently tapping it 10 times. Not that much. But anyway, I mean, if you can afford to do multiple sweeps, then we know that SGD will work well. But in these online settings, that's not always feasible. Okay, so just to show its scales, we went to slightly harder, and this is still still very small stakes, but a little harder than Moon. So it's function n is 10-dimensional classification, and this is error rate versus number of observations. This is on a holdout test set, and so our low rank method is in blue, and then the replay SGD is in green, and there's a pretty healthy gap, and that's after tuning, hyperparameter tuning very carefully. The diagonal approximations, you can't really see them. They're in the dotted line here. And that's basically the same as like online gradient descent, which is what I claimed earlier. The diagonal approximations really don't work better than point estimators. Okay, but one of the cool things, so why do we work so hard? So, okay, we converge a little faster in the online setting. But there are other tricks you can use. Like there are higher order optimization methods you could use. But because we have a posterior, we can do Thompson sampling or active learning, as I illustrated. And the other thing you could do is we can model changing distributions, which is related to the thing I talked about at the beginning of the talk. Well, there we were adapting the prior in an unsupervised way using EM. Here we're adapting the model at runtime in a supervised way using common filters, right? So it's a different solution to a somewhat similar problem. So here the problem is that it's a toy problem, but it's used in the literature. Like God intervenes at every 300 steps and shuffles all the pixels in your image and completely randomizes the distribution. And now you're expected to predict class labels from that. So every time there's a shock to the system, then the error rates go back up to chance, and then the systems all evolve and they start learning under this new distribution. And you can see that the low-fi rank 10 approximation adapts the fastest. So it's squeezing the most statistical juice out of the data. Modulo computation, a reasonable computation time, right? There are other techniques, Monte Carlo techniques, that do outperform this, but they're very slow. Okay, so popping up a level, I would say this decision-making under uncertainty field, and particularly sequential decision-making, is really interesting. It's very, very rich. There's a lot of room for, I think, innovative methods that model uncertainty in a tractable way, and you can use your uncertainty to guide your decisions about what kind of data collect or experiments to perform. All right. I know I'm watching the clock here. So that was pillar 2. Pillar 3, they do get shorter and shorter. So what is pillar 3 about? Well, this is about, so in statistics, so prediction is sort of what basically, until recently, is like the only thing people in machine learning cared about, more or less. And people in statistics cared less about prediction and cared more about, here's a gob of data, please tell me something interesting about this data. So often they will fit very simple models to the data, but these models are domain specific and they mean something to the domain practitioner. And they want to interpret the coefficients, perhaps as representing some causal quantity. And that's basically just model fitting, maybe with some uncertainty estimation associated with it. And there's like 1 billion books written on this, and it's beautiful. But I think of this as more of an analysis problem where you're given some data, maybe it's supervised, maybe it's not. And what you're interested in is analyzing that data by fitting a posterior distribution to it, where in this case, the posterior are over the parameters of a predictive model. But this predictive model is interpretable. It's not a black box neural network. There's no point modeling posteriors over neural net parameters because if you want to interpret them, because they don't really mean anything. But if it's a linear model, then it's easy to understand. Well, this could be a more complicated scientific simulator, but the point is you're doing posterior inference over parameters of some meaningful model. So if we think about that from a decision theory point of view, what are we doing? Well, now the unknowns are the parameters. The data, the observation are all the data. The action is your parameter estimator. The action is the estimates, and the loss is whatever, like L2 loss. So now the optimal thing to do, if we want to minimize L2 loss, is again the posterior mean, but it's the posterior mean over our parameters instead of the output. So the difference, the key difference from supervised learning is that you never observe the parameters. So you can't assess performance by measuring the discrepancy between prediction and truth because you never see the truth. It's hidden, right? So you have to trust your model. And now if your model is correct, this is the optimal thing to do. But you need other methods to do model validation, like holdout prediction tests. So that's analysis where we're inferring parameters. In machine learning lands and in some statistical applications, the unknown variables there's one unknown variable per data case, right? So these are then called latent variables. So for every xi, we have a zi or zi, and maybe that just represents, let's say the data are just points in R2, and the z's are the colors, and they just represent cluster centers. So we're just doing clustering. Or maybe the data is like high-dimensional molecules, and then we're going to, for each molecule, we assume there's a point in some low-dimensional space, and we're trying to learn that mapping into the low-dimensional space. So we're doing manifold estimation. And so for that, you might use something like a variational autoencoder. So there it's the same setup. It's a similar setup, right? If we think about that from a decision theory point of view, for every x, there's an unknown z, and we want to estimate the z's for every single data point, right? Rather than a fixed dimensional vector, a fixed dimensional parameter vector. So here, in these kinds of problems, it's harder to come up with a, like in the prediction problems, it doesn't matter so much what the form of your predictive model is. I mean, it does to a certain degree. Like, you know, CNN might be better than an MLP, might be better than a decision tree if you're doing image classification. But if you have enough data, then even an MLP will work. And this is why transformers are magic, right? Because in the big data regime, these models are very flexible and they all work more or less the same. And it doesn't matter so much what the model is, it matters more about your data. And this is like the bitter lesson of deep learning. But if you're doing unsupervised data analysis, then you very much care about the form of your model because you're going to be staring inside the bowels of that model. So that model better mean something to you because the whole point is you're trying to understand this data set through the eyes of a model that you trust or that you believe in. So that means every problem needs its own model. And then that's like a rich playground for statisticians to churn out papers and have fun. So this is a paper I wrote a long time ago where I'm not going to go into the details, but there was some biosequence data and we created a bespoke model for it, some HMN variant. And my student, one of my first students, Saurabh Shah, who's a biology expert, like he could then navel gaze into the posterior estimate and read out signals that meant something biologically and then go verify it into the lab. So, you know, this is really cool. But this model family is rather limited. It's like a hierarchical HMN. More recently at Google, we were trying to analyze videos of rats in cages running around for some life science application. And we wanted to infer behavior. This is in conjunction with Calico. So we wanted to infer their behavior and see if it correlated with various drugs that they were taking or other biological conditions. So we wanted a state space that was much richer, that was both discrete and continuous. And we wanted to learn that in an unsupervised way from video. And we weren't interested in generating beautiful videos to put on YouTube. We're interested in finding concise explanations of the underlying data source. So videos of rats in cages are too complicated for an intern project. So we simplified it to like a dot running around, but it is still a video. But it's the key signal is more about the motion than the appearance. So if you stare at this, you can come up with all kinds of stories about the generative data generating process here, right? But it's kind of like something like a car on a racetrack where it's like going on a straightaway and then it turns and slows down and it's like some mixture of simpler pieces, right? So we wanted to decompose the signal into a set of locally compact representations that were easy to interpret. So we came up with some nonlinear switching dynamical model, and this is intractable to fit. So then we came up with some amortized variational inference scheme that I won't have time to talk about, that is kind of fancy. And then you do all the work, and then you can use it to fit these videos and pull out state estimates that are meaningful. And like if we applied it to some motion capture data, and so this is the input, and so it's like 80-dimensional. And then it discovers 3 underlying states, which are basically spinning around and then like doing dancing in one place, then you curve, and then you dance in one place, and then you swirl around again. So it's spiritually similar to the other example I mentioned earlier. And in synthetic data where you know the truth, like we outperform other methods. Anyway, so sorry that was so rushed, but you can ask me later if you want to know more details. I would say popping up a level once again, this analysis area, this unsupervised learning area, super interesting if you have like a meaningful scientific model and you want to invert it. And you want to use, say, neural nets to speed up. You either like learn a neural surrogate or you want to do data-driven posterior estimation where it learns a proposal distribution, for example. So I think this is very interesting. And it's again, I think there's room to, like, if you're depressed because like you think ChatGPT has solved all the world's problems. It hasn't, right? Like if you actually want to do science, you need to think about the problem, and the problems have very specific models, and they're often quite difficult to fit. So I think there's still room to innovate there. Okay, so the last thing, talking of ChatGPT and big models, the last pillar is synthesis. So in analysis, we're given high-dimensional data, we squeeze it into a low-dimensional space, and we stare at that space and hopefully learn something. In synthesis is basically just generative AI. So we just want to create high-dimensional outputs. And this could be because we're creating images, maybe we're creating weather forecasts, maybe we're creating text dialogues. Right, so from a decision theory point of view, basically what's the setup? So there's an unknown world state, which is what is the desired output? What image should I generate? Like, let's say I'm given a prompt C and some caption, and I want to generate an image that goes with it. I don't know what the right image is. So the unknown state of nature is the optimal image that goes with this caption. The policy is my image generator. My action is a sample from my policy. And then the loss is, I don't know, what is the loss? So it's not clear. This is like one of the biggest problems with generative AI is it's not clear what the loss function should be. So here's an example, right? So let's say we want to generate images given a prompt. So I type in a prompt, toilet paper with real cactus spikes. And with enough magic, you get images like this coming out. This is from the imaging system. And this is really amazing, right? But so this is X hat. This is the output of my system. The true X is unknown, right? I don't know what the right, and maybe this is the image that was labeled as the training set. I don't really know how to measure quality in this way, right? So you just have to like pay humans to learn some proxy reward function. And that's basically what people do, because it's not, in these high dimensional spaces, it's not really clear what an optimal action is. And it's certainly not one-to-one. There are many, many images that would be equally satisfying to a user. Similarly, in the text space, right? Like, how do you quantify the quality of a dialogue? It's very, very hard. So that's a big problem. So that's so calling it a decision theory problem is a bit of a stretch, but leaving that aside, then there's the modeling issue. How are we going to create these high-dimensional outputs? Well, there's a whole zoo of models you can use. And like, here are some members of the zoo. And there's a chat, I've a chat from each one of these zoo animals in my book. I only have 5 minutes, so I'm not going to go through this, but you can do autoregressive models and diffusion models, and we have some hybrid approach that was published recently, and you can get great results, and it's really fun. And sometimes you have to work pretty hard on the prompt to make it behave, but with enough work, you can make these things do magic. And I can't really say much more anyway, because it's all secret. So conveniently, that brings me to the end of the talk. So just to summarize, with this sort of decision theoretic point of view, it's pretty flexible because you can vary what it is you mean by the hidden state, what it means you mean by the observations, what it means for the action space, and what the loss function is. And if you wiggle those axes, you can basically cover all of machine learning. That's how you can make sense of it all. And that doesn't cover everything. I mean, there are other topics that are sort of orthogonal to these 4 axes, like generic things like optimization and inference. And then there are other things like systems and scaling and privacy and all of that stuff that I don't know anything about and therefore didn't talk about, but they're also important. Okay, that's it.
Thank you very much, Kevin. We have time for 1 or 2 questions, maybe. For those of you that won't get fortunate enough to ask Kevin yourself, I will plug that he's going to feature on the department's podcast later today. It's called Sample Space, so you can look that up, and Nico's going to conduct the interview. Anyways, do we have 1 or 2 questions for Kevin? Everybody's very shy. Yes, the gentleman in the back.
Thank you very much. LLMs can't come up with any new data from these big models. Actually, whether you're any of these current types can come up with something that is legitimately novel, just the kind of concatenation of the facts. Whether we need something like
I mean, LLMs do come up with things that are not in the training set, obviously, right? I mean, and these big models in general, right? Like, so DALL-E 2 is a tokenized image generator. So it's basically an LLM in token space. And it's creating, these images are not on the web. I mean, now they are, but, and so these models, these big models clearly generate things outside of the support of the training set. They're not just concatenating training points, but they do it in a kind of uncontrolled way. So I think that's the theme of this talk was like all of the models I presented, I kind of bespoke models that are small and boutique almost, which has pros and cons. The pros is if you trust that model, then it's going to generalize in a way that you believe, like maybe you've injected prior knowledge from physics or whatever. So when it generalizes, it makes a climate forecast for the next century, you have reasons to believe that because it satisfies the laws of physics by construction. Whereas an LLM, maybe it will, maybe it won't. So it will generate cool pictures, but should you trust it? I don't know. I'm not sure I trust them. Is it inspiring and cool? Yes. So yeah, that's what I'd say to them. If you have a checker on the output of your LLM, like a program induction or whatever, or a math theorem prover, then you're fine. As long as you have a way to verify the output, then you can get best of both worlds. Yeah.
So you talked about how, like, the better lesson of deep learning was that you just use more data. But the models we're training now are using kind of all the data that humanity's ever generated on the internet. And so do you think that the way forward is going to be like new ways of generating or synthesizing data, or are they going to kind of switch into a new era where it's actually better methods as opposed to the data that leads to better modeling?
It depends on the problems that you're tackling. There are some areas where you're fundamentally data limited, like even in the health space for privacy reasons or whatever, and in many scientific applications. The data, you just can't inhale the web because the web doesn't have the data that you need. So there are questions you can't answer by pre-training massive models because they're just apples and oranges. So yeah, so if you work on those problems, then you're protected to some degree. Yeah. Oh yeah, we'll do one live, one online.
Yes. Let's take these two questions and then we'll wrap it up.
So you mentioned the importance of developing the directional scientific discovery to aid scientific discovery, and I was wondering about like the implications of especially within Spurious Correlations and distribution shift, how there's a lack of data that's pointing towards the scientific discovery direction, and more towards say standard images and text classification. Do you think that's a specific reason behind that data?
I think so. In the sciences, the main challenge is this sort of unsupervised learning stuff, right? Like this kind of thing. So there's problems with data access, but I think even more fundamentally, there's problems with evaluation. So let's suppose I've got 10 gazillion molecules and I fit some absolutely massive VAE to it, and it reconstructs the data perfectly. How do I know it's any good? I know nothing about chemistry. So now I actually have to go talk to my chemistry friends. And then how do they know it's any good, right? So they have to go do an experiment, and that takes a year. And machine learning people can barely wait a week, right? So there's just a huge mismatch between, I think it's primarily eval problem, right? So if you say, well, I can then generate future molecules, then you can, but then you maybe don't need this latent model. You can just do it directly in token space, and that's what people do. So if it's in data space, then you can evaluate it, but that might not give you any insight about the mechanism.
Let's have a quick look. David, if you can hear us, you can also unmute yourself and ask your question. And then I think we need to get out of here because I'm already stretching someone's patience.
Oh, okay. David?
Okay. Can you hear me okay? I'm wondering if anyone has ever tried incorporating in a loss function the CO2 emissions involved in these immense numbers of calculations. If all it's doing is counting the number of times you click on an advertisement, I'm not convinced that the effect on net zero is worth it.
So there are people who worry about the carbon footprint of deep learning, and there are papers on that. In my opinion, it's massively overblown. It's basically negligible compared to flying. I mean, I flew here from the US, guilty. You know, I think transport and concrete production and farming and all of these other things are way more significant than deep learning. Deep learning is a drop in the ocean in terms of energy consumption and greenhouse gases. So I don't think the companies, they're more worried about the cost of serving these models. So there's an economic incentive to make them more efficient, whether or not it helps the environment. So I'm not really worried about that. I think it's just smoke and mirrors.
Trouble is, everybody says that. Okay, thank
I mean,
you.
I'm worried about other things to do with the climate. I'm just not worried about that. On the contrary, I think these models might be quite helpful. Like, one last word. Like for molecule design, there are people using not just deep learning, but machine learning more generally for optimizing batteries and solar panels and organic chemicals, or organic molecules to increase efficiency of alternative energy sources. And so that's, you know, so they burn carbon to power GPUs to create energy devices that then become more efficient that they can then use to power the GPUs. So, you know, it'll basically, you go into debt, like getting your mortgage, and then it pays off in the long term. So you have to spend a little to save a lot, I think.
All right, let's thank everyone.